let's talk about planes. Good old planes, okay? And if we're going to talk about planes in space, I want you to refer to this picture. Hopefully you've printed out your notes, because pretty much everything I say, I've tried to type it up for you, because I know it's hard to grasp everything I'm saying. Okay, so in the last section, we did lines. And we figured out that in order to represent a line, all we needed was a point and a direction. So now I need to figure out, how do I write the equation of a plane in space? Now, if I just had a vector parallel to the plane, that doesn't help me convey what direction this plane's going. So one of the things we're going to be using is we're going to be looking at a plane, and we're going to be looking at this new vector called n, which is perpendicular to my plane. So wherever my plane is, this vector is coming straight out of the plane, and it's orthogonal, right? Remember, that's our new fancy word for perpendicular, okay? So in order to determine a plane, we're going to need a point on the plane, all right, initial point, and we're going to need this orthogonal vector n, whatever he is. All right, so now let's set up how we're going to come up with our equation. Okay, so P is an arbitrary point in the plane, any point, pick one, there it is, okay? Then we're going to create two vectors. We're going to let R be the vector from the origin to that arbitrary point, and we're going to let R sub 0 be the vector from the origin to our initial point, okay? And then, of course, we have we can find the difference of these vectors, right? R minus R sub 0, okay? Which is going to be the vector right here, okay? And it connects the initial point to the arbitrary point, okay? So far, so good? Okay, this normal vector is orthogonal to this vector. Agreed? Yes, yeah, because that's how we created the normal vector. So we could say that the dot product of this vector and this vector is equal to, perpendicular vectors, their dot product is equal to, okay, someone said it's 0. I heard you, believe it or not. Or maybe it was a cat. Oh, I don't know. Okay, so the normal vector n is perpendicular to every vector in the plane. So in particular, it's normal to this one we made up, R minus R sub 0. And if you want to, you could rewrite this equation. Remember, the dot product is distributed. So n dot R minus n dot R sub 0 equals 0. Move one to the other side of the equation. These two sets of equations are called vector equations. And I usually use them in this form. And you'll see why in a minute. Because one of the things I'm going to do is I'm going to rewrite these vectors in component form. Okay? All right, so here's my vector equation of a plane. I need my normal vector. I need a vector to an arbitrary point and a vector to my initial point. Okay? So to get a scalar equation, okay, one that we could actually work with, I'm going to start with, let's say the normal vector is the vector ABC, or we said is going to be the vector to XYZ, and R sub 0 is the vector that goes to the initial point. Okay? So, this was our equation, right? N dot R minus R sub 0. So I'm going to start by making the vector R minus R sub 0. And remember, to make a difference of vectors in component form, we just subtract the components. Okay, so here's N dot the difference. So X minus X sub 0, Y minus Y sub 0, Z minus Z sub 0. Okay, and remember, this dot product must be equal to 0. Now, we remember how to do a dot product, right? Multiply the components and add them. So first component times first component plus second component times second component plus third component times third component. Okay? So this is the scalar equation of the plane through our initial point with this normal vector. Okay? So when we write it like this, it's the vector equation because it's written in vectors. This one's called the scalar equation because it's written with scalars, with numbers. Okay? All right, ready to try an example? Sure, you have nowhere to go, right? Nothing to do? Yeah. My cat's sitting here sunning himself. Looking forward to this example. Okay, so finding an equation of the plane through the point 2, 4, negative 1. So remember, this is my initial, right? With normal vector n equal to 2, 3, and 4. So this is my, what I am calling my A, B, and C. Okay? Well, just remember your equation. I always like writing the equation. You don't have to, but I like to. Sometimes by rewriting things, I tend to remember them. And with my advanced age, well, that's important. Okay, so there, this is my scalar equation. All right, so A is 2x minus the x coordinate plus B, y minus the y coordinate plus C, z minus the z coordinate. Minus a minus makes a plus. And one of the things we could do to what I just wrote is distribute, collect all my constants together, and I can rewrite this as 2x plus 3y plus 4z equals 12. So all I did was move the constant to the other side. Okay? Now, the next thing it asked me to do is find the x-intercepts. Well, we know how to do x-intercepts. So if I want to find the x-intercept, I need to let the others be 0. So let y and z be 0. Well, when y and z are 0, I find that x is 6. To find the y-intercept, I let the others be 0. All right? So if we let x and z be 0, we find the point 0, 4, 0. And the z-intercept, again, let the others be 0. Oops, x equals, y equals 0. So 0, 0, 3. Okay, so we're going to plot the point 6, 0, 0, 0, 4, 0, and 0, 0, 3. And we're looking at the plane that goes through them. And, well, since I can't draw, here you go. That is a graph. And this plane continues out in all directions, right? But it's hard to, you know, if I just colored it all blue, then you wouldn't see the plane. So this is the plane that goes through these three intercepts. Okay? And there's one other way of writing the equation of a plane, which is the one I just did where, right, at the end of the example, I rewrote it like this with the constants all over on one side. Okay? That's called the linear equation when I collect all my terms. And the constant could be on either side. On this side, the 12 looked easy on the other side. Okay? And that's called a linear equation.